Next question, the function f is a differentiable function and satisfies the functional equation f of x plus f of y is equal to f of x plus y minus xy minus 1 for every xy belonging to R. If f of 1 is equal to 1, then the number of integers n not equal to 1 for which f of n is equal to n. So, we are given a functional relation f of x plus f of y is equal to f of x plus y minus xy minus 1 for all xy belonging to R, for all xy belonging to R, and it is also given that f of 1 is equal to 1, and it is given that f is a differentiable function, and we need to find for how many values of n f of n is equal to n. So, to do this, because f is given to be differentiable, let me assume y to be a constant for a while independent of x and differentiate the equation with respect to x, or partially differentiate the equation with respect to x, treating y to be independent of x. Derivative of f of x is f dash of x plus f of y is a constant, derivative of f of y is 0 is equal to derivative of x plus y, f of x plus y is f dash of x plus y, minus derivative of xy is minus y and derivative of 1 is 0. So, we have f dash of x is equal to f dash of x plus y minus y for all xy belonging to R, for all xy belonging to R. So, this functional relation is also true when f x is 1. This functional relation is also true when x is 1. So, let us put x equal to 1 here, or even this is true for x equal to 0. Let us put x equal to 0 here. F dash of 0 is equal to f dash of y minus y. F dash of 0 is equal to f dash of y minus y, or throwing y the other side, f dash of y is equal to y plus f dash of 0, which is a constant. F dash of y is equal to y plus f dash of 0. So, f dash of y is a linear, f dash of y is a linear. So, f of y is going to be a quadratic, f of y will be a quadratic, and f of y minus y equal to 0 will be a quadratic equation. F dash of y is a linear, so f of y will be a quadratic, f of y minus y equal to 0 will be a quadratic equation. So, this equation is a quadratic equation, and we are already given that 1 is the root of this equation, f of 1 is given to be 1, f of 1 is given to be 1. We have to find how many roots are there for the equation f of n minus n is equal to 0, f of n minus n equal to 0, how many such integers satisfy. Now, we can see, because this is a quadratic equation, there will be 2 roots, there will be 2 roots satisfying this, and already 1 is counted. So, we will have one more root for this equation. So, we will have one more root for the equation f of n minus n is equal to 0. We can simply integrate and also find out, but from the logic of f dash y being linear, f of y minus y being a quadratic, directly we can say this will have one more root other than 1. So, answer is option B. Next question, let f of x is equal to x minus sin x and g of x is equal to x minus tan x, where x belongs to 0 to pi by 2. Then, for these values of x, f of x into g of x is greater than 0, f of x into g of x is less than 0, f of x by g of x is greater than 0, and option D, none of these. This is a very important question. F of x is defined as x minus sin x and g of x is defined as x minus tan x for all x belonging to 0 to pi by 2. For all x belonging to 0 to pi by 2. And we need to talk about the sign of f of x into g of x, which we can talk when we know individually the signs of f of x and g of x. Look at the inequality. In 0 to pi by 2, sin x will always be less than x will always be less than tan x. This is a very important inequality. For all x belonging to open 0 to pi by 2, sin x will be less than x less than tan x. We can prove this using monotonicity. F of x is equal to x minus sin x. Consider this as a function. F dash of x, this is a continuous differentiable function. F dash of x is 1 minus cos x. 1 minus cos x is always non-negative. It is 2 sin square x by 2, or cos x will is always less than or equal to 1. So, 1 minus cos x will always be greater than or equal to 0. So, f of x is a strictly increasing function. F of x is a strictly increasing function. For all x greater than 0, f of x will be greater than f of 0. For all x greater than 0, because it is a strictly increasing function, f of x will be greater than f of 0. So, x minus sin x we can say will be greater than 0 minus 0, which is 0, or x will be greater than sin x. X will always be greater than sin x. Similarly, looking at g of x, g dash of x is 1 minus secant square x, which is minus tan square x, which is always less than or equal to 0. So, g of x is a decreasing function, and because g of x is a decreasing function and x is greater than 0, g of x will always be less than g of 0, and g of 0 is 0. So, x minus tan x will be less than 0, or x will always be less than tan x. That is how we have this standard inequality, sin x less than tan x. So, from there we can say f of x is always positive and g of x is always negative. So, f of x into g of x will also be negative. F of x into g of x will be negative. It is option B. Next question, if f of x is equal to x cube plus bx square plus cx plus d and 0 less than b square less than c, then in minus infinity to infinity, option A, f of x is a strictly increasing function. Option B, f of x has a local maxima. Option C, f of x is a strictly decreasing function. And option D, f of x is bounded. So, for the function f of x is equal to x cube plus bx square plus cx plus d, given that 0 less than b square less than c, 0 less than b square less than c, we have to discuss on R if f of x is bounded. Option C, a cubic function can never be bounded. As x tends to plus infinity, this tends to plus infinity x cube, and as x tends to minus infinity, this tends to minus infinity. So, f of x will take all values from minus infinity to plus infinity. It is a onto function on R, it can never be bounded. So, answer cannot be option D. Now, we have to see whether it is among A, B, C. For all of the options, because f of x is a differentiable function, we need to talk about strictly increasing, decreasing nature and local maxima and minima. Let us observe f dash of x. Differentiate 3x square plus 2bx plus c is f dash of x. Look at option C. F of x is a strictly decreasing function. For f of x to be strictly decreasing, as this is differentiable function, it is mandatory that f dash x is always less than or equal to 0. F dash x is always less than or equal to 0. But because coefficient of x square is positive, This will never be possible. So again option C cannot be our option. So we are left with option B or A. Either the function has to be strictly increasing or it needs to have a local maxima. Observe f dash of x, it is a quadratic 3x square plus 2bx plus c. For f of x to be strictly increasing, f dash x should be greater than or equal to 0 for all x belonging to R, and a quadratic will be greater than or equal to 0 for all x belonging to R only when its graph is above x axis, that is when its discriminant is less than or equal to 0 and coefficient of x square is positive. Coefficient of x square, already we can see it is to be positive. Now let us observe discriminant. Discriminant of f dash of x is b square, that is 4b square coefficient of x square minus 4ac, a is 3, c is c. This quantity should be less than or equal to 0. So b square should be less than or equal to 3c. B square should be less than or equal to 3c. Now it is given that c is a positive number and b square is less than c. So if b square is less than c, then automatically b square will also be less than 3c. So discriminant is negative, coefficient of x square is positive, f dash x will be greater than or equal to 0 for all x belonging to R. That makes f of x a strictly increasing function. So answer is option A, f of x is strictly increasing function. Next question, f of x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, so on up to x power n by n factorial. Then f of x is equal to 0 where n is odd and greater than or equal to 3. Option A cannot have any real root. Option B cannot have any repeated root. Option C has one positive root, and option D none of these. We have to observe the function f of x is equal to 1 plus x by 1 factorial plus x square by 2 factorial, so on up to x power n by n factorial. N is given to be odd. And n is given to be greater than or equal to 3, and the options are option A, f of x cannot have a real root. Option B, f of x can't have a repeated root. Option C has one positive root. F of x has one positive root, and option D none of this. Now n is given to be odd, so this is a odd degree polynomial, and odd degree polynomial, every odd degree polynomial will have at least one real root. Every odd degree polynomial will have at least one real root. We can explain this logic with complex roots. Whenever they occur in pairs, z and z bar, alpha and alpha bar. So we cannot have all odd, all n imaginary roots. They can only be in even numbers, so at least one root has to be real. Moreover, range of odd degree polynomial is R. Odd degree polynomial is onto on R. So f of x equal to 0 will have at least one solution. So option A cannot be our answer. Option C has one positive root. Now we can see all plus signs, and assuming that there is a positive root alpha, 1 plus another positive number plus a positive number plus a positive number, so on up to all positive numbers can never sum up to 0. So it is again never possible to have a positive root. It can't be option C. Option B can't have a repeated root. Let us see if f of x can have a repeated root. Let alpha be a repeated root of f of x. If alpha is a repeated root of f of x, alpha will satisfy this equation. Alpha will satisfy this equation. If alpha is a repeated root of f of x, alpha will also be a root of f dash of x equal to 0. Alpha will also be a root of f dash of x equal to 0. F dash of x is what? Derivative of 1 is 0. Derivative of alpha is 1. Derivative of alpha square is 2 alpha. 2 gets cancelled. We have alpha by 1 factorial plus derivative of x cube by 3 factorial. Derivative of x cube is 3x square. 3 gets cancelled. X square by 2 factorial. So, alpha square by 2 factorial. So on up to x power n by n factorial. On differentiation, n gets cancelled. X power n minus 1 by n minus 1 factorial is equal to 0. For this equation also alpha is a root. So alpha satisfies both 1 plus alpha by 1 factorial plus alpha square by 2 factorial, so on up to alpha power n by n minus 1 factorial equal to 0, and it is also satisfies 1 plus alpha by 1 factorial plus alpha square by 2 factorial, so on up to alpha power n minus 1 by n minus 1 factorial equal to 0. So sum up to this is also 0 and this sum is also 0. That makes it alpha power n is 0. Alpha equal to 0 should be that common root. So if at all there can be any repeated root, that has to be alpha equal to 0. But can alpha equal to 0 be a root of this equation? No. When alpha is 0, 1 plus 0 cannot become 0. So alpha equal to 0 cannot be the root of the equation. So option B is absolutely true. The function cannot have any repeated root. So it's answer B. Next question. If f of x is equal to sin x plus a square x plus b is an increasing function for all values of x, then option A belongs to minus infinity to minus 1, option B, A belongs to R, option C, A belongs to minus 1 to 1, and option D, none of this. If f of x is equal to sin x plus a square x plus b is an increasing function for all x belonging to R, then we need to find the values of a. For all x belonging to R, this is an increasing function. So f dash of x, because sin x, a square x, b are all continuous differentiable functions, for a function to be strictly increasing, it is necessary and sufficient that f dash of x, which is cos x plus a square, to be greater than or equal to 0 for all x belonging to R. For f of x to be increasing on R, f dash of x should be greater than or equal to 0 for all x belonging to R, equality not forming any interval. Now if we want cos x plus a square to be greater than or equal to 0 for all x belonging to R, even for the least value of cos x, this expression should be positive. Even for the least value of cos x, this expression should be greater than or equal to 0. So even when cos x is minus 1, that is a square minus 1 should also be greater than or equal to 0. Once this is true, for every other value of cos x, automatically expression will be positive. So a square should be greater than or equal to 1, or a should belong to minus infinity to minus 1 closed interval union closed interval 1 to infinity. A square should be greater than or equal to 1, and for that a should belong to minus infinity to minus 1 union 1 to infinity. So among the available options, a subset of this is given in one of the options, which is answer A. So A is the right answer for this question. Next question. If f of x is equal to x square e power minus x square by a square is an increasing function, then for a greater than 0, x lies in the interval option A closed a to 2a, option B minus infinity to minus a union 0 to a, option C minus a to 0, and option D none of this. It is given that a is positive, and we need to check for what values of x is the function f of x is equal to x square e power minus x square by a square an increasing function. For what values of x, this is this function an increasing function. So, let us find f dash of x. Differentiate 2x e power minus x square by a square, 2x e power minus x square by a square plus x square into derivative of e power minus x square by a square, e power minus x square by a square into derivative of minus x square by a square, which is minus 2x, that makes it 2x cube by a square. This quantity for the function to be strictly increasing, f dash of x should be greater than or equal to 0. F dash of x should be greater than or equal to 0. So, let us see what all things we can take common. 2x into e power minus x square by a square we can take common into 1 minus x is taken common. So, we are left with x square by a square. This quantity should be greater than or equal to 0. Now, e power whatever will always be positive. So, e power whatever will always be positive. It has no contribution in the sign. You can be happily removed. 2 also has no contribution in the sign. We can happily remove it. So, x into taking LCM a square minus x square by a square should be greater than or equal to 0, or x into x square minus a square should be less than or equal to 0. Taking LCM, a square minus x square, minus of it is x square minus a square. So, if this is greater than or equal to 0, x into x square minus a square should be less than or equal to 0. We can factorize it. X plus a into x minus a should be less than or equal to 0. Applying wavy curve method, a is a positive number. So, first comes minus a, then comes 0, then comes a, positive, negative, and we want the expression to be less than or equal to 0, that is in minus infinity to minus a union 0 to a. So, x should belong to minus infinity to minus a closed, or x can even belong to 0 to a for the function to be strictly increasing function. So, among the available options, you can see option B matches with the right answer. Answer is minus infinity to minus a closed union 0 to a. Next question, let f of x is equal to modulus of x minus 1 plus modulus of x minus 2 plus modulus of x minus 3 plus modulus of x minus 4 for all x belonging to R. Then option A, x equal to 2 is a point of local minima. Option B, x equal to 3 is a point of local minima. Option C, x equal to 1 is a point of local minima. Option D, none of these. So, let us see, f of x is given as mod x minus 1 plus mod x minus 2 plus mod x minus 3 plus mod x minus 4. We have to find the points of local minima for this function. We have to find the points of local minima for this function. Let us cut x axis at 1, 2, 3 and 4. Let us cut the x axis at 1, 2, 3 and 4. When x is less than 1, x minus 1 would be negative, x minus 2 would be negative, x minus 3 would be negative, and x minus 4 would be negative. So, modulus of x minus 1 is 1 minus x, modulus of x minus 2 is 2 minus x, modulus of x minus 3 is 3 minus x, and modulus of x minus 4 is 4 minus x. So, f of x would become 1 plus 2 plus 3 plus 4, 10 minus 4x. So, f of x would be 10 minus 4x, and at x equal to 1, functional value will come out to be 6. So, this function is a straight line up to x less than 1, having slope minus 4, So it's a decreasing function. So this is how the graph would be. Between 1 to 2, x minus 1 is positive, x minus 1 is positive, x minus 2 is negative, x minus 3 is negative, x minus 4 is negative. So the function would become x minus 1 plus 2 minus x plus 3 minus x plus 4 minus x. 1x and x gets cancelled. X minus 1 plus 2 minus x plus 3 minus x plus 4 minus x. So we have 8 minus 2x, function as 8 minus 2x between 1 to 2. 82, this becomes 4, and at 1 it will be 6. It is a continuous function. So it is a straight line joining these 2 points. Let us look at the function between 2 to 3. When x is between 2 to 3, x minus 1 is positive. So mod x minus 1 is x minus 1. X minus 2 is also positive. So mod x minus 2 is x minus 2. X is between 2 to 3, x is less than 3. So mod x minus 3 will be 3 minus x. Mod x minus 4 will be 4 minus x. We can see this x gets cancelled. 7 minus 3, that makes it 4. So it's a constant function 4 from 2 to 3. From 2 to 3, it's a constant function. Similarly, completing the graph, it becomes 6. There will be symmetry about 5 by 2, x equal to 5 by 2. It becomes again 6 when x is 4, and again it will be an increasing function after x equal to 4. So this is the graph of the function. This is the graph of the function. It's kind of a bucket. So we can see this function has no local minima. There is only global minima for all points between 2 and 3, but there is no local minima. There is no local minima for this function. Let us see why. At 2, left hand limit, left hand side function values are more than f of 2, but right hand side function values are equal to f of 2, which violates the condition of local minima. All the values in the deleted neighborhood should be more than f of 2 for it to be a local minima. All the function values in the neighborhood should be more than f of 2. So this is not a local minima. Even x equal to 3 is not a local minima, and x equal to 1 is again not a point of local minima. Left side values are more and right side values are less, so it can't be a point of local minima. So none of these are local minimums, or there is no local minimum for this function. It's option D. Next question, if a and b are real numbers such that x cube minus ax square plus bx plus 6 equal to 0 has its roots real and positive, then we need to find the minimum value of b. Look at the function. F of x is x cube minus ax square plus bx minus 6, and the equation f of x equal to 0 has its roots real and positive. Roots of this equation are all real and are all positive. So we need to find the minimum value of b. We need to find the minimum value of b. Let's say all the real and positive roots are alpha, beta, gamma. Alpha, beta, gamma. Let's say they are the 3 positive real roots of this equation. From the given equation, sum of the roots we can see alpha plus beta plus gamma is equal to a minus of coefficient of x square by coefficient of x cube. Alpha beta plus beta gamma plus gamma alpha, sum of the roots taken 2 at a time is minus of minus b plus b, and product of the roots alpha beta gamma is minus of minus 6 plus 6. Alpha beta gamma is 6. Alpha beta plus beta gamma plus gamma alpha is b. Alpha plus beta plus gamma is a. Now, because all the roots are positive, let us apply harmonic mean AM greater than or equal to GM greater than or equal to HM, geometric mean will always be greater than or equal to harmonic mean. Geometric mean on 3 numbers alpha, beta, gamma is cubed root of alpha, beta, gamma will always be greater than or equal to the harmonic mean. Harmonic mean is 3 divided by 1 by alpha plus 1 by beta plus 1 by gamma. Let us take LCM and simplify this. 3 LCM would be alpha, beta, gamma. It goes to the numerator. Alpha, beta, gamma divided by alpha, beta plus beta, gamma plus gamma alpha will always be less than or equal to cubed root of alpha, beta, gamma. Now we know alpha, beta, gamma is 6. So let us replace this by 6. 6 power 1 by 3. This is also 6. Alpha, beta plus beta, gamma plus gamma alpha is B. So this quantity is B. So we can see B is always greater than or equal to 3 into 6 power 2 by 3. Once 6 power 1 by 3 gets cancelled, we will be left with 6 power 2 by 3 here. B is greater than or equal to 3 into 6 power 2 by 3, or the minimum value of B is 3 into 6 power 2 by 3, or 6 square is 36, 3 into 36 power 1 by 3. So the correct answer is option C. Next question, if f of x exists for all x belonging to R and g of x is equal to f of x minus f of x whole square plus f of x whole cube for all x belonging to R, then option A, g of x is increasing whenever f is increasing. Option B, g of x is increasing whenever f is decreasing. Option C, g of x is decreasing whenever f is increasing. So given that f of x exists for all x belonging to R, we need to talk about monotonicity of the function. G of x is equal to f of x minus f of x whole square plus f of x whole cube for all x belonging to R. To talk about monotonicity of this function, let us differentiate g of x. G dash of x is derivative of f of x, f dash of x, derivative of f of x whole square 2 into f of x into f dash of x, plus derivative of f of x whole cube 3 into f of x whole square into f dash of x. Taking f dash of x common, we have 3 f of x whole square minus 2 f of x plus 1. 3 f of x whole square minus 2 f of x plus 1. Now we can observe f of x is real for all x belonging to real, and discriminant of this quadratic, this is a quadratic in terms of f of x, and discriminant of this quadratic is negative. B square is 4, minus 4ac is minus 12, minus 8, discriminant is negative. So this quadratic is always positive. Whenever irreducible quadratic with coefficient of x square positive, we have that quadratic always to be positive. So irrespective of the functional value, f of x value, this is always positive. Now if f dash x is positive, g dash x would be positive. If f dash x is negative, g dash x is negative. So if the function f of x is increasing, then g of x will be increasing, and if f of x is decreasing, g of x will be decreasing. So among the available options, it is g of x is increasing whenever f of x is increasing. Option A. Next question, cosine of the angle of intersection of the curves y is equal to 3 power x minus 1 log x and y is equal to x power x minus 1. We need to find cosine of the angle of intersection of the curves y is equal to 3 power x minus 1 into log x and y is equal to x power x minus 1. Now let us see, to find angle of intersection between the curves, first we need to find the point of intersection. So we need to find a point which both the curves satisfy. 3 power x minus 1 into log x, we want it to be equal to x power x minus 1. So we need to have some log 3, and then we cannot see any log here. So probably point of intersection should have something which makes these quantities zeros. So log x will become 0 when x is 1. So let us try if x equal to 1 satisfies this equation. 3 power 1 minus 1 is 0, 3 power 0 is 1, into log 1 is 0, 1 power 1 is 1, minus 1 is 0. So 1 satisfies this equation. So point of intersection is x equal to 1, and at x equal to 1 y coordinate is 0. So point of intersection is 1 comma 0, and at the point of intersection, to find angle of intersection, we need slope of tangent for one curve, slope of tangent to another curve, and from there we can find angle between the tangents, which will give you angle of intersection of the curves. So for the first curve, y dash is differentiate UV rule 3 power x minus 1 divided by x plus log x into derivative of 3 power x minus 1, which is 3 power x minus 1 into log 3. Derivative of a power x is a power x log a. So y dash is 3 power x minus 1 by x plus 3 power x minus 1 into log 3 into log x, and we want y dash at the point 1 comma 0. Put x equal to 1. 3 power 0 is 1, 1 by 1 is 1, log 1 is 0. So this quantity entirely becomes 0. So y dash is equal to 1. So slope of tangent for the first curve, it is 1. Let us call it m1. m1 is 1. For the second curve, y dash is equal to derivative of x power x into 1 plus log x, logarithmic differentiation, x power x into 1 power log x, minus 1 derivative is 0. So y dash is x power x into 1 plus log x, and we want y dash at the point 1 comma 0, that is when x is equal to 1. So 1 power 1 is 1, log x is 0, so this becomes again 1. So m2 is also 1. m2 is also 1. That means the tangents are same, the curves touch each other. The curves, they do not intersect, they touch each other at 1 comma 0. So angle of intersection is 0, both the tangents are parallel, they are coincident. So angle of intersection is 0, and cosine of angle of intersection cos 0, we know it is 1. So answer is 1, which is option A. Next question, the equation 8x cube minus ax square plus bx minus 1 equal to 0 has 3 real roots in geometric progression. If lambda 1 is less than or equal to a less than or equal to lambda 2, then the ordered pair lambda 1 comma lambda 2 can be. It is given that the 3 real roots of the equation 8x cube minus ax square plus bx minus 1 equal to 0, they are in GP. Roots of this equation are in GP. So we can assume the roots to be alpha by r, alpha and alpha r. 3 numbers in GP, we can always assume them as alpha by r, alpha and alpha r. Now observe product of these 3 numbers, r and r gets cancelled. Product of the roots is alpha cube. Product of the roots is alpha cube. And from the equation, product of the roots is minus of constant term. In a cubic equation, product of roots is minus of constant term divided by coefficient of x cube, which is minus 1 by 8 plus 1 by 8. So alpha cube is 1 by 8, or alpha we can say it is half. Alpha is half. So alpha we can replace it by half. We can assume the roots to be 1 by 2 r, 1 by 2 and 1 by 2 r. Now we need to talk about the values of A. We need to talk about the values of A. A is equal to sum of the roots. Sum of the roots is how much? Minus of coefficient of x square, that is A, divided by coefficient of x cube 8 is sum of the roots, which is equal to 1 by 2 into r plus 1 by r plus 1. R plus 1 by r plus 1. Now let us cancel this half on both sides. A by 4 is equal to r plus 1 by r plus 1. R plus 1 by r plus 1. Now r plus 1 by r, sum of a number and its reciprocal. Sum of a number and its reciprocal. We know this will always be greater than or equal to 2 or less than or equal to minus 2. So we can say A by 4 will always belong to minus infinity to r plus 1 by r is less than or equal to minus 2, plus 1 will be less than or equal to minus 1, minus infinity to minus 1, union 3 to infinity. R plus 1 by r will either be greater than or equal to 2 or less than or equal to minus 2. Adding 1, r plus 1 by r plus 1 will either be between minus infinity to minus 1 or from 3 to infinity. Multiplying by 4 throughout, A belongs to minus infinity to minus 4 union 12 to infinity, or among the available options, answer is option C. Next question, on the interval close 0 to 1, the function x power 25 into 1 minus x power 75 takes its maximum value at the point. Option A is 0, option B 1 by 4, option C 1 by 2 and option D 1 by 3. We need to check at which point in closed interval 0 to 1 the function f of x is equal to x power 25 into 1 minus x power 75 has its maximum value. That is, what is global maximum in the interval close 0 to 1. We know global maximum can occur at critical points or at the end points. F of 0 and f of 1 are both zeros. F of 0 and f of 1 are both zeros, and as x lies between 0 to 1, 1 minus x is positive, x is positive, and f of x is positive for all values of x in open 0 to 1. So somewhere we will definitely have in between a global maximum value. This is a bounded function with f of 0 and f of 1 to be 0, and in between the function is positive. So there should be some global maximum in between, and that will occur at critical point. So let us look at all the critical points. F dash x, f of x is a differentiable function. For a critical point, f dash x has to be 0. Differentiate it, UV rule, x power 25 into derivative of 1 minus x power 75, 75 into 1 minus x power 74 into derivative of minus x is minus 1, plus derivative of x power 25, 25 x power 24 into 1 minus x power 75. From these two, we can take 25 common and also x power 24 common, and also 1 minus x power 74 common. We are left with 1 minus x here, and we are left with minus 3x. We have taken 25 common, so 3 is left and 1 x is left, minus 3x. So f dash of x is equal to 25 into x power 24 into 1 minus x power 74 into 1 minus 4x. So there is only one critical point between open 0 to open 1, which is when this is 0, that is x equal to 1 by 4. So, at this point we should have global maximum. So, answer is x equal to 1 by 4, option B.